Hello, my name is Adam Gray, and welcome to this lesson, lesson 4.2, Data Distributions. And as you'll find, this lesson is one that is maybe a little bit simpler than its name even suggests. Data distributions might sound like we're about to see a lot of college-level statistics problems, very challenging, full page of scratch work type problems. But that's not what we're going to see here. Because what's most likely to be tested on the MCAT in terms of data and data distributions are simple concepts of data, things like mean, median, mode, range, and so on, but in more critical thinking contexts. They'll ask you to apply those terms, those statistical measures to data that they'll give you from a passage, for instance. And that's exactly how we're going to see them in context here. The learning goals for this lesson are both to use those common measures of central tendency, all of those standard deviation, interquartile range, etc., to describe data, specifically data that you would find in MCAT passages, and also to recognize anomalous data. Anomalous data is also known as outliers, which is a term you might be a little more familiar with, and we will see one practice question about that as well. The science topics that we will see this in the context of are learning and memory. Learning and memory are, of course, in their own right, very important for success on the MCAT, but we won't really be diving into this content here. It's merely that the passage, in context of which we'll see all these questions, is about the concepts of learning and memory. And because questions like this, skill 4 questions on data distributions and their aspects, are most likely to be attached to passages, that's exactly what we're going to do. We've got one passage here on this page. It's got these few paragraphs and then this table. And so the first thing that needs to be done here is read the passage and outline it, just like you would on test day. So go ahead, read this passage, label each element to make a full outline. There should be a framework for that outline right in the facing page of your book. Then we will see a sample outline, go through this paragraph by paragraph, and get into those questions. So let's move through this paragraph by paragraph to get a good outline. This first paragraph is a classic background paragraph, and the background that it gives us is on learning curves and the way that they are studied. Learning curves meaning the more you experience something, the more you practice it, the better you get at it. So just learning curves, background. You could say it's experience versus skill. You build skill while you get more experience. In the second paragraph, we learn about the exact example of learning curves that this passage is going to focus on, and that is specifically running rats through a maze. And we get a basic experimental setup and an interesting detail that instead of measuring how fast the rats run the maze, researchers look at how many dead ends or mistakes that a rat runs into, therefore implying that a lower score, fewer mistakes, means a rat has more skill at the maze. So a good label here would be just that we have the experimental design of these rats and mazes experiments. Paragraph 3 gets a little bit more in depth, especially into the mathematics of these rats in a maze experiment, and we get an equation, which in our case is definitely going to be important to questions, and on test day it's probably going to be important to questions on the passage as well. The equation we get here is an equation for L. The L stands for learning in this case, and it relates to N, which is defined as the number of mistakes. So what this equation does is it takes the number of mistakes and uses a transformation, 1 over n plus 1, to turn it into L. And the strength of this is explained earlier on in the paragraph, which is that turning it into L makes it positive, makes the curve positive. It means it will go up as experience goes up rather than down as mistakes would go down. Some good labels for these then are the definitions we get in paragraph 3, and then of course to diagram out the equation as well, that we should define what these major variables are. L is the learning variable, N is the number of mistakes. Then finally, the top of the screen is actually the end of the previous paragraph, but this is all the data. This particular study that we're going to be focusing on in almost all of the upcoming questions is about these 5 rats in a maze. They do 8 trials each, and it's recorded the number of mistakes that they've made. So in review, this is the full passage outline. And as with other passage outlines, it's not like you're going to get all the questions wrong if yours is a little bit different than this. What's important is that you take away the fact that we first get introduced to this concept of learning curves, then the specific experiment that's looked at in this passage, which is rats and mazes. Important to note, either in paragraph 2 or paragraph 3, that learning is measured by the inverse of mistakes, a definition of the equation for L, which takes n as an input and brings out a positive trend rather than a negative trend, and then finally all of the data in table 1. That's going to be a good basis with which to start attacking these questions, so let's get into them now. Here's question number 1. And if you read the question stem, there is a big statistics skill 4 word called out, and that is mean. And here, the word mean, it means the average, the statistical average, meaning the sum of a set of values over the number of values. And this question is asking us to do a calculation of a mean. It's asking us to calculate capital L for rats running through the maze a 4th time. Now, capital L is exactly that variable that got defined in equation 1 of the passage. L equals 1 over n plus 1, and we're told to look only at the 4th time. So here, trial 4. Now that you do know where to look and what formulas to apply to this question, go ahead and try to answer it. So let's check out the calculation steps here. In order to calculate the average for trial 4, what we need to do is plug each of the values in that column into the formula for L. The 4 values in trial 4 are 9, 4, 9, 9, and 9. And if you plug those into the formula 1 over n plus 1, all of the 9s become 1 over 10, because it's 1 over 9 plus 1, and the 4 becomes a 1 over 5, 1 over 4 plus 1. So the full average formula is 1 over 10 times 4 plus 1 over 5 all over 5, because there are 5 total values. If you work out all that math, it becomes 3/5 over 5, or 3 over 25, making the answer B. And this question is a really good example of how the MCAT could test these subjects on test day. Once you know what to look at and what formulas to use, this question is a relatively simple plug and chug. But the challenge to this question is knowing where to look, knowing what formulas to use, and doing it quickly. One mistake a lot of students make the first time they see this question is that rather than using the formula for L, they just find the average of the 4 values of n. 9 plus 4 plus 9 plus 9 plus 9 all over 5, and that would work out to 8. Answer choice C. That is by far the most tempting trap answer of these 4. Now, if you didn't fall for that trap answer, good work. But if you did, make sure you know why. Namely, you probably overlooked the fact that it asked for L and not for N, and both of those variables were defined in the passage, and try not to make it next time you see a question like this. So that'll be our one big example of how the MCAT might test mean. Let's move on to another measure of central tendency. The mode of a set of data is the most common or most frequent number in a data set. That means that if you have a data set of 1, 2, 2, 2, 2, 5, 6, the mode would be 2. And similar to how we saw mean being tested in number 1, mode, even though it is a relatively simple concept in its own right, will almost always be tested with a little twist. And that's what we see in this question too. Before we see the full worked out answer for this, give it a try. Read number 2, follow the full question attack strategy, and pick an answer. So number 2 does mean that we have to try to find a mode, or maybe even several modes, but it tells us to do something first. It says the data gets standardized by removing the most mistake-filled run for each rat. And then we're asked how many modes does the full set of data have. We're going to remove 5 data points, then we're going to have a whole lot of data points left, 35 actually, and need to find out how many modes that set has. So the way to solve this question is first to remove the highest value for each rat. For rat number 1, that is 11, and you can remove either one of those 11s, it makes no difference. For rat number 2, it's the 13, rat number 3, it's the 15, rat number 4, it's the 11, and rat number 5, it is the 15. Then, and this does take a little bit of careful attention to detail, you need to find the most common numbers. And if you were able to count carefully, you probably found that 4, 7, 9, and 11 all appear exactly 5 times in the data that's left. And no other numbers appear more often than that. That means that this data set actually has 4 modes, and that's fine. A data set can have multiple modes, but it means the answer is D, that the data set that's left has 3 or more modes. Now note again that what made this question difficult wasn't the content or the statistics being tested, but the critical thinking and integration of knowledge that you needed to make. It's just another piece of proof that careful reading and attention to detail are going to get you more points on test day than anything else. And that brings us to question number 3, which is asking us about standard deviation. Now, 2 previous statistical terms we saw, mean and mode, were measures of central tendency. Standard deviation is known as a measure of dispersion, or how far apart a data set is. And boy, oh boy, does it have a pretty complicated formula if you're going to calculate out the whole thing. But here's the good news. It's down at the Kaplan tip at the bottom of your page, bottom of your screen, which is it is really unlikely that the MCAT will require you use that crazy formula of standard deviation, big square root, big capital sigma, all that jazz. Rather, the most important thing you have to bring to bear to questions like this, if you see them on the test, are the general definition and trends of standard deviation and other measures of dispersion. Namely, the basic definition of standard deviation, that a set of data points that is more spread out, farther apart, means a larger standard deviation. Ones that are more scrunched up together is a smaller standard deviation. So with that information in hand, go ahead, head back to the data. Here's the data you'd need from trial 1 to trial 8, and get all the way to an answer for this question. So one of the first things you might have noticed, and if you did, good job, was that these 4 answer choices are really similar to one another. In fact, the first line of each answer choice only differs by 1 word. Choices A and C say less deviation, and choices B and D say more deviation. And then the second line of each answer choice is pretty similar too. So that means just like every other question with very similar answer choices like this, you are going to bring yourself pretty far towards an answer just by eliminating based on those small differences. So if you head back to the data, with a little bit of analysis, you can see that trial 1, its lowest number is 10 for rat 4, and its highest number is 15 for rat 3. For trial 8, its lowest number is 2, and its highest number is 4. And now, while standard deviation is certainly more complicated than just looking at the highest and lowest number, it is still true that looking at the highest and lowest number is a really good indicator if all you have to say is which one is bigger. And in this case, trial 1 has more deviation. But that means that for what the question asks, namely, how does the mistakes per run change from trial 1 to trial 8, it's that deviation goes down. Starts high and ends low. That means we can eliminate choices B and D right away, just based on the third word of each answer choice. Now, using process of elimination on the last 2 choices, there are, again, only a few very small things different between these. Choice A says it decreases from 13 down to 3, and choice C says that standard deviation decreases from 2 to approximately 1. And this is the place where you might have said to yourself, oh wow, do I really have to use that crazy formula? I don't know how to use that. And perhaps unsurprisingly, based on the explanation given when we first brought up this question, no, you don't have to use that entire formula. And that's again because of the basic concept of what standard deviation is. It's a measure of how spread out a group of numbers is. Roughly speaking, it's a way of saying if you take 2 random numbers from a set, how far apart are they? So if a data set has a standard deviation of 2, that means if you take 2 random elements from it, they're probably about 2 units apart from each other. And what that means is that this part of choice A, the fact that it's saying, wow, the standard deviation is starting at 13, should really leap out to you as strange. We already saw that the very highest to the very lowest number of trial 1 are only 5 units apart. That means the standard deviation is going to be way smaller than 13, meaning that regardless of any calculations you might do or whatever you think about choice C, choice A has to be wrong and choice C has to be right. And in fact, that is true. Now, if you want to meticulously plug in each of these trials into the standard deviation formula to prove to yourself that choice C is correct, then you can. And there's definitely enough resources in especially your books to let you do that and make sure you're doing it right. But I really want to emphasize you should not sweat that point. If you have a question about standard deviation on your MCAT, it's going to be a lot like this one. And you can walk into that question knowing there's going to be some way out of any hard calculation that it looks like you might have to do. Number 4 here is more directly about the graphical representation of a hypothetical set of data. The graph here at the right side of your screen is really just a visual aid for you to answer this question. If you had a question like this on test day, they may or may not supply a graph like this. Either way, we'll use it to help us out a little bit here. As we work through this question, the equation from the passage will probably be a little bit of help too. So go ahead, work through this full question, and bring it to an answer. Now, this question has some fascinating mathematical and statistical underpinnings to it, as we'll see. But just like the last question, question 3, and any other question on the MCAT, you've got to assess the question before you really get into the weeds of trying to solve it. And that also means assessing the answer choices. And again, just like question 3, these answer choices all follow the same pattern. Each choice has a phrase, a comma, and then another phrase. The first phrase is about how steep the curve is, and the second phrase is about the maximum value of what L might be. That means that even though the question itself is pretty open-ended, a little bit challenging, asking about the average slope, the question is necessarily made a little bit easier by the fact that its answer choices are so formulaic, and you should use that to your advantage. And now that we see that in the answer choices, it reveals the very fastest, most efficient way to get to this answer. And that's to consider which one to look for first. Should we look at the slope, or should we look at the maximum value of L? Well, the slope, as you probably know from your coordinate geometry, is delta y over delta x, rise over run, but maximum value is just a single value. All the things being equal, figuring out a single value is probably easier than figuring out something that's a formula, like slope. So let's start with that maximum value. Now, here's where this gets a little bit fun. Even though this question doesn't ask you for an exact maximum value of L, you can find out the exact maximum value of L, and you're going to find it out using this formula. And if you haven't already, use that formula to figure out what is the very, very largest value L can be. We know that N is the number of mistakes that a rat might make in a certain maze. And the fewest number of mistakes you can make is 0. That means the lowest N can be is 0, and the highest L can be is 1 over 1. That is, this graph asymptotically approaches the value of L equals 1. And this is a fact intrinsic to L as a number, as we've defined it. Meaning it's not going to change however many mistakes are made over time, however hard or easy the maze is. And that's what this question does. It asks us about a hard maze and an easy maze. That means L is going to have the same maximum value no matter what the maze. And as luck would have it, there's only one answer choice that says L would have the same maximum value. It's answer choice A. And honestly, since your goal on test day is just to get points, if you had this question on test day, you should pick A and forget about the rest. But now, of course, every single question that's about this topic might not bail you out quite so easily. So let's see briefly why A is correct and the average slope for a longer, more complicated maze would end up being less steep than one for a short maze. Well, it's because if, as the question stem says, the rat stops running the maze once it has a perfect trial, a trial with 0 mistakes, that means that a harder maze is going to take more trials to reach that perfect run, whereas an easy maze is going to take the average rat fewer trials. If a maze is really easy, a rat might even get it right on the first or second try, whereas if it's a hard maze, it might take them 9 or 10 tries, or even more. And since slope is delta y over delta x, and the number of trials in this case is what's on the x-axis, that means a hard maze is generally going to go farther along on the x-axis than an easy maze, meaning we're making the denominator of the slope equation bigger. If you make the denominator bigger, you make the slope itself smaller, meaning that indeed, as answer choice A says, the curve on average would be less steep. Now, there's one more piece to recognize about this question that might have tripped you up when you picked an answer. And that was, you might have thought, well, hold on, a hard maze is going to have a steep learning curve. That's just sort of a phrase that's worked into our vernacular, that hard things have a steep learning curve. The MCAT, for instance, has a steep learning curve to it. But honestly, it doesn't matter how we talk about learning curves in our everyday life if, as with this question in this passage, the MCAT defines something a certain way, as it does with this one. You've got to go with that definition. And if you're careful about outlining passages and reading questions carefully and moving systematically through them, you'll be able to catch those on test day. This question brings in the third major measure of central tendency. You might have thought it was missing earlier, in fact. We had a question on mean and a question on mode, but we had left out median. Well, here it is. The median, in case you need a quick refresher, is the middle number of a set of numbers if you put them in order from smallest to greatest. And if there's an even number of numbers, that means if there isn't one single middle number, there's kind of two numbers that are tied for the middle number, then you take the average of those two middle numbers. With that knowledge definitely in hand, go ahead and answer this question. Now, this one might have been the most straightforward that we've seen so far, though you probably did a good bit of work on your scratch work trying to find the median for each rat, and that's fine if you did. The median, if we start with rat number 1, means that we have to order the trials from least to greatest or greatest to least, but least to greatest is a good standby, which ends up looking like this. Then we can do the same for rats 2, 3, and 4. And, well, one piece of good news is we don't have to do it for rat 5 because there's only 4 answer choices and rat 5 isn't an option, so we don't have to think about him. Then you find the median of each of these sets, meaning you narrow things down to find the middle value crossing out both top and bottom, and this is one of those data sets where we're going to have to take the average of the two middle numbers. Take the average of the two middle numbers of each of these. Honestly, you might even be able to do it without calculation if you visualize it like this. It becomes pretty clear that rat number 2 has the lowest median than any of his compatriots. In fact, it's much lower. Rat number 2 had a really good set of trials. Maybe he's some kind of superhero rat. Now, this rat's pedigree is clearly outside the scope of the MCAT, but the real takeaway here is that even though to do this question right, to do it the way that we did it, it takes a little bit of time, a little bit of writing, a little bit of scratch work. If you know how to do it and it's content that you know, like medians, and you commit to doing that scratch work, you can get it right. Almost 100% certainty. And those are questions that you shouldn't put off, even though they take a little scratch work and a little time. They're questions you should do right away when you're triaging on test day. That's the strength of content that you know and being able to identify that it's content that you know. It lets you move through the section faster and get more questions right more quickly. Question number 6 throws out just one more of those measures. This one, like standard deviation, is a measure of dispersion. It's called interquartile range. We get asked for rat 4's interquartile range in the data. And interquartile range has a really big word in there, but you should think of it like this. You're probably familiar with the median, at least you probably are now after you did question 5, and maybe you think of the median as a midpoint of the data, the middle number if you put it all in order. Well, the quartiles, which are an important part of interquartile range, are not really the midpoints, but the quarter points of the data. Meaning rather than just one point in the middle separating data into two pieces, you've got 3 points where you cut the data to separate it into 4 equal pieces. And the places where you cut those data are Q1, Q2, and Q3, the first 3 quartiles. In order to apply that definition to this question, we do need to go back to the trials themselves. Here are the trials for rat 4. And just like we did with the median, we have to take these numbers and put them in order. Then, because the quartiles are the quarter points of the data, Q1 is right here, 1/4 of the way in. Q2 is here. Q2 is also equal to the median, actually. Q3 is here, and Q4 is, well, Q4, you're very unlikely to get a question about it, but Q4 is defined as just the maximum value of the data. We know the quartiles have to be in these 4 places because this is a set of 8 data points. So if you're going to split a set of 8 data points into 4 quartiles, into 4 equal segments, each of those segments, first one, second one, third one, fourth one, are each going to have 2 items in them. Finally, just like for the medians, if there's a tie for which number is the quartile, as we have here, both in Q1 and also in Q2, you take the average of those two numbers that are tied. Then, back to this question itself, it's asking for the interquartile range. And that itself is another defined term. The interquartile range, or the IQR sometimes, is Q3 minus Q1. Q3 in this case is 10, Q1 is 6.5, and so the answer to our question is 3.5, 10 minus 6.5. Note here that even though this question did require you to do calculation, it was all very simple arithmetic, proving once again that Skill 4 data-based questions about measures of central tendency and dispersion are much more so about your knowledge of the concepts and applying them to the questions than it is about doing any sort of hard math. And that brings us to our seventh and final question. This one's all about the last word of the question stem, the outliers. This one, try on your own. Read the question, work your way through the data in the Roman numerals, and pick an answer. Now, one interesting fact about these answer choices is that literally every answer choice contains Roman numeral 2, that is trial number 4, and you might not have noticed that. If you ended up getting the right answer, which you'll know in a moment, then it's okay if you didn't notice it, but it does mean that ultimately there's no reason to evaluate trial number 4. It must have a significant outlier in there somewhere, since it's in every single answer choice. But then the basic definition of the outlier, it is what it kind of sounds like. An outlier lies outside of the general bulk of the data. It means that in groups of data like trial 4, the number 4 really stands out as kind of a weirdo among all those 9s. And in trial 7, that 11 is really big compared to the other numbers in the trial. If you will put those numbers in order, it's 3, 4, 5, 6, 11. Really kind of out of place. That means that this answer is indeed answer choice C. And if you have a question about outliers on your MCAT, it's going to work very similar to this. It should stand out very strongly if there's an outlier, and if so, how many there are and which pieces of data they actually are. There are, if you're a statistician or know a statistician, some formal definitions, quote unquote, for what an outlier is. That is 1.5 interquartile ranges from the bulk of the data, or 4 standard deviations from the mean, but those are not things you have to memorize. Just the definition of an outlier. If it's really far away from the bulk of the data, either on the high end or the low end, and it looks a little lonely, then that's an outlier. And that is the end of this lesson on data distributions. Remember, the two basic concepts, which we saw a bunch of terms connected to, were centrality, that is, what is the middle of the data, and also variance, how spread apart is the data. We saw the mean in question number 1, where the formula is the sum of the values divided by the number of values. We saw the median later on, where we ordered items from least to greatest and found the middle number. We saw the mode, which is the most common number in a set. And the question that we did actually had multiple modes. There's also a term here called bimodal. It's a specific case if there are exactly 2 modes or spikes of data. That's called a bimodal data set. We then saw some measures of variance or spread outedness of the data. The first being standard deviation. Larger standard deviation means spread out data. And if you ever see a reference to the variance of a set of data, variance is just the square of standard deviation. Standard deviation squared. So larger variance means more spread out data. Then we saw quartiles, which are a lot like medians, but rather than splitting the data into 2, they split it into 4. And the interquartile range, which is the difference between Q1 and Q3. Just like other measures of variance, larger interquartile range means a more spread out data set. And then finally, outliers. Outliers are numbers that are just far away from all their buddies. And now that you finished this lesson, you should be a little bit more comfortable with Skill 4 questions on test day. Remember, Skill 4 questions as a whole are going to make up 10% of your score on all the science sections. That may not sound like a whole lot, but as you've seen in this lesson, a little bit of knowledge of concepts can go a long way towards being really confident and really quick on questions like this. So it's very much worth your time to understand these concepts well and know how to apply them.